Okay, so then we should move forward to Charles Fletcher. Charles Fletcher is a PhD candidate in Oxford, also working with Daniel and Michael Moody. And his talk will be on CASRA, a tool for 3D modeling of future operation and reconstruction.
Thanks for the thanks for the introduction, Marcus. My internet's being a little bit patchy, but hopefully it won't cut out. So yeah, today I'm here to talk about CASRA, which is a simulation tool I've been developing during my PhD. Let me see if I can actually go to the next slide. Oh, there we go. Okay. CASRA is a tool for simulating specimen evaporation in full 3D during atom probe experiments. And these simulations, because they're basically modeling the tip as a continuum rather than at an atomic level, these simulations are quite fast, like under 20 minutes on a sort of standard laptop. And basically, another additional factor of these simulations being so fast is that they can be used to actually directly drive the atom probe reconstruction, which I'll talk about in a bit. So there's just an example of the simulation of a low field precipitate and its subsequent reconstruction. You can see the sort of narrowing distortion that occurs. So a quick breakdown of what CASRA does. So the sort of first step in the sort of procedure would be to set up the model geometry. And this can be done either through analytical functions that are provided by part of a module, or actually you can sort of load in a tip geometry, an experimental geometry using electron tomography. And then you go ahead and simulate the specimen evaporation using CASRA. And then following this, you sort of can calculate the ion trajectories. And then basically, once a termination condition's reached, such as the size of the specimen, it'll either, if this hasn't been reached, it will iterate and continue evaporating the specimen. And if it has, then it will output data. And this output data is in the form of a VTK format, which is a sort of standard computer graphics format. And POS files as well for the sort of simulated reconstructed data. And then a number of additional tools are also provided in the package, one of which is to perform this model-driven reconstruction. The other is to just perform standard point projection reconstructions on simulated data. And then finally, there's some tools to calculate composition and density throughout your reconstruction. So the first thing that you can use CASRA for, which is pretty straightforward, is that just sort of some simple comparative modeling with experiment. So basically, yeah, the idea is you can use CASRA to understand physical distortions that are observed in experimental data. So by setting up your model geometry to resemble microstructure you might be seeing in experiment, you can basically generate synthetic data of the APT experiment and then reconstruct it and sort of compare the distortions that are occurring with the experiment to sort of better understand where the distortions are coming from. And the additional feature, this model-driven reconstruction, so basically CASRA models the specimen evolution, and you can actually use this instead of assuming a hemispherical apex during the reconstruction. And theoretically, this can correct for distortions due to evaporation field differences. So this is still quite early work, but basically by calibrating the model times to experiment times, sort of the index, the sort of ion arrival time, or the index in the sort of evaporation sequence, and then basically making some assumption about the model geometry or your specimen geometry, you can correct the reconstruction. So there's this sort of there's this narrowing in the central channel within the standard point projection reconstruction, which is due to a low field phase down the center of the central channel. And then basically using the model, you can correct for this once you've calibrated the fields and the times between the model and experiment. So setting up the tool is fairly simple. So the code can be found here. And then basically this can run on both Ubuntu and Windows 10 using the Ubuntu terminal, which is available through the Windows App Store. The tool can be directly used from the command line or as a Python package. So the back end is written in C++ and compiled Python. The front end is Python. And then, yeah, it's fairly easy to install and set up. So README is provided. The installation pretty much consists of two lines. One just to install the dependencies of the package and the other one just to compile the code. And then introductory tutorials are also available as IPython notebooks on the repository. So these cover simulation setup, running of simulations, and tools for data processing and reconstruction. So in summary, CASRA is a tool for simulating and solving distortions in atom probe experiments. It allows for fast simulation of realistic specimen shapes. And basically these models, another benefit of sort of these simulations being sufficiently quick is that you can use these models to directly drive the reconstruction process. Thank you for listening.
Okay, so are there questions to Shots on the line? Yeah, great talk. Thank you. Shots. Are there questions to CASRA, the use of CASRA and the integration into tools? Yeah, there's one from Benjamin Kaplan's.
Where's there a question? Sorry, what's the? Can you model voids? Yes, you can. So basically, the method of simulation uses something called the level set method, and this allows you to basically track or model the joining and separating of curves or surfaces. So yes, this basically allows you to model voids. And actually, I've got a paper that's in press. I think it should be coming out sometime in the next 24 hours, at least the accepted manuscript, which talks a bit about modeling voids using CASRA. But yeah, that is definitely something you can do.
Can I ask a question? Are you planning on doing any kind of modeling of the detection process?
So not at the minute. So at the minute, I've just been focusing on kind of the distortions that are arising. But yeah, I guess you could model the detection process. The other thing, I guess, is also investigating kind of a generalization for the Ball correction. As in now we know what the shape of the emitter is. You might be able to try and correct time of flights using that information.
Yeah, that's actually a really good idea.
So can you do iterative reconstruction to minimize error? It comes from Andrew Protein.
So not at the minute. But currently the model basically assumes the geometry. So you can iteratively reconstruct varying the evaporation fields. But at the minute the geometry is fixed, but you could in theory do a similar procedure where you kind of what's called shape optimization, where you basically change the geometries of the phases over time and then try and match up the reconstruction to the model you started with. So yeah, you could do it, but I've been looking at iterative reconstruction, varying evaporation fields, but just keeping the sort of the specimen geometry fixed at the moment.
Can I have a question?
Yeah, Peter. Yeah.
A lot of the level set method would depend on the quantization of the surface, essentially directly on a triangulation. So how do you make sure that a triangulation is fit for an accurate representation, essentially, of the field distribution on the surface? Because I can see you have some adaptive meshing here, right? At the shank, it's a little bit coarser.
Yeah.
And
So I'm using Seagull to do the adaptive meshing. It's basically, it runs as an isotropic remeshing algorithm in Seagull. And that basically ensures that the mesh is well conditioned for the electrostatic solver.
So it's based on an octree then, probably.
Yeah.
Is that what it does?
Yes, I think I'm not exactly sure. But yeah, I think it's based on some tree-based method. And then yeah, the isotropic remeshing, you can kind of remesh at different sizes down the shank.
Have you had a look in the numeric variations at sort of the larger elements? What kind of variations would happen there? Because there could obviously be in pinch points, you could have numeric instabilities, essentially.
Yes, so I have a little bit, not in too much detail, but yeah, it is something that does arise, that if you have too big, if you sort of your triangle size increases too rapidly down the shank, then you do end up with a very poor quality solution at the apex. So yeah, it becomes very poorly conditioned, the problem.
Okay, so
yeah,
okay.
the tricks.
Yeah, just make.
Go ahead.
Go ahead, Charlie.
Oh yeah, I was just saying. So at the minute, I'm kind of just manually tuning it to ensure that the sort of the solution near the apex is well conditioned.
Okay.
Great.
So yeah.
I think we should move on with that, Marcus.
Exactly.
If that's all right. Great, thank you.